Greetings, everybody. This is Dr. Krishna Kalluri, alternate counselor from the Southern California section of the American Chemical Society, abbreviated as SCALACS. And it is my pleasure today to welcome Sarah Tolbert, professor of chemistry at UCLA. And before I introduce her formally, I would mention a few sentences about the Chemist Celebrate Earth Week, abbreviated as CCEW. The Earth Day was first officially recognized on April 22nd, 1970, as a way to demonstrate support for a healthy environment, raise awareness about environmental issues, and remind people that we all need to contribute to a sustainable planet. ACS joined the Earth Day celebration in 2003, and ever since there have been annual CCEW events. The ACS established the CCEW public awareness campaign to promote the positive role that chemistry plays in the world and in our lives. And CCEW is administered by the ACS Office of Science Outreach, which is part of the Education Division. The Committee on Community Activities serves as the advisory group for outreach programs and selects and develops the CCEW themes and materials. This year, the theme is Get a Charge Out of Chemistry, with a focus especially on batteries. I can go on with the history of CCEW forever, but I would stop at that, and I will introduce Prof. Sarah very briefly and very quickly so that I won't cut in too much into her time. She is a distinguished professor in the Department of Chemistry and Biochemistry and Material Science and Engineering at UCLA. Her research focuses on controlling nanometer scale architecture in solution processed nanomaterials to generate unique optical, electronic, magnetic, structural, and electrochemical properties. She has published over 200 scholarly research articles and has 20 patents focusing on electrochemical energy storage, organic electronics, nanomagnetics, nanoscale control of thermal conductivity, and new ultra-hard materials. She also serves as the faculty director for a program aimed at bringing nano concepts to schools, students, and general public throughout the greater LA area. Professor Tolbert is the recipient of a number of awards, including the American Chemical Society Henry Storch Award in Energy Chemistry, a Fellow of the Royal Society of Chemistry, an NSF, or the National Science Foundation Special Creativity Award, the ACS R.A. Glenn Award, and the UCLA Diversity, Equity, and Inclusion Award. She directs the DOE Energy Frontier Research Center on synthetic control across length scale for advancing rechargeables. And we are glad to announce that she is the recipient of this year's Tolman Award, and we are looking forward to the event in which we actually give the award to her sometime in June, I presume. Now, without much ado, I would like to pass on the mic to Sarah.
Okay, thank you so much. Can everyone hear me? Yes, we're good?
Yeah, I can hear you.
Okay, excellent. It is a pleasure to welcome you to my office and to this talk, where I hope to talk to you a little bit about what chemists can do to help solve problems in energy science. And in particular, we're going to focus on porous materials, which I will call Holey materials for this talk. Okay, so this is Earth Week. Happy Earth Week to everyone. Hopefully you are all thinking about what chemistry can do to help our planet. And one of the themes of this year's Earth Week, Earth Month is plastics and recycling. And so maybe you thought we can help develop biodegradable plastics. We can help develop ways to recycle better. These are great things for chemists to do, but they are not what I am going to talk about. What I'm going to focus on is energy and the fact that we have the potential to make much more of our energy usage based on renewable energy. And we also have the potential to cut our greenhouse gas emissions by the electrification of the transportation industry. So if we ask, what do all these things have in common? Well, the use of renewable energy and the use of electric vehicles are tied together by a challenge that faces the whole energy industry, which is the fact that we need better energy storage. So if we look at this picture, we see a lot of solar cells and a lot of wind turbines. And in California, these are two of the most prominent forms of renewable energy, and they're making a huge impact on our overall energy usage. The problem is that some forms of renewable energy, and in particular solar, do not produce the most energy when we need them the most. So this is a graph of net electricity load. So what we need in California, this is for California, and it's over the springtime, averaged over the springtime period when we have lots of sunshine, but it's not too hot. And what you find is that in the middle of the day, when the sun is shining, in 2015, the energy usage was pretty flat. But as we have built in more solar across California, we have found that the net electricity load has dropped to the point where it is actually negative. Negative means we have energy we have to get rid of and we don't know where to put it. So we actually have excess electricity. We can sometimes have to pay people to get rid of the extra electricity that is coming in from all of their solar panels. So the reason that we have this midday challenge can be seen if we look at this graph of energy generation over daily cycles. And this is from right now, from middle of April. That's the data that's up on the web and available. What you see is that some forms of energy, like natural gas, are fairly constant across the day. Wind is variable, but it's randomly variable. Wind blows when the wind blows. But solar is very predictable, and it is at points our largest source of energy. So we get a lot of electricity when the sun shines and no electricity when the sun does not shine. The result of this is, if we now move to the graph on the right, in blue is the net electricity demand for California, and in yellow is the net electricity generation. And we find that in the middle of the days when the sun's out, not when it's cloudy, but when the sun's out, we generate more than we can use. And that's what leads to these curves on the bottom where we actually have net negative electricity generation. That's us trying to get rid of our electricity. So some of it we pass off on the grid to the Pacific Northwest or the desert Southwest. That's good, except that there's a lot of losses in moving electricity long distances across the grid. The other thing that we could do with that extra electricity is we could store it and use it later in the day when we don't have a lot of electricity. And so if you are a chemist like me and you say energy storage, you will immediately think of a battery as the best way to store energy. But it turns out that on the grid, that's not normally what happens. The vast majority of energy storage on the grid, like 95%, is something called pumped hydro, or when you have extra electricity, you use it to run a pump that literally pumps water uphill. And when you need extra electricity, you let that water flow back downhill and you run a generator. The problem with this is it's not terribly efficient, and it also has a big environmental impact in that you need not one, but two large reservoirs conveniently separated by a large steep hill. So this is not available in all locations, and it also has an impact on the environment. So what we would like to do is to be able to get more electricity onto the grid in the form of batteries. But there's a problem, and that problem is that right now, the batteries that we have available do not do the things we need to get onto the grid. So what would be the ideal properties? So by far the biggest problem is that batteries are too expensive. So we need them to be lower cost, and that means we need to make them out of earth-abundant components. We just need to bring the cost down. Combined with that is that we need batteries that have very long lifetimes. That means you can charge and discharge them many, many times. These two things together produce the overall cost of a battery, because its actual cost is the cost to make it amortized over the number of times you can charge and discharge it. We would also like them to be easy to recycle. There's a lot of new effort in recycling batteries. We would like them to be high capacity so that you don't need to build as many batteries to store as much. And we would like them to be fast charging. And you may ask, why is fast charging on this list? And I'm going to try to show you why fast charging is really a key component of green energy storage. So today I'm going to focus on charging speed and cycle lifetime. And I'm going to try to show you why Holey batteries are a great solution to that problem. Okay, so why is fast charging a key component of clean energy future? Well, one of the key reasons is that we would like to electrify the transportation industry. It is one of the largest forms of CO2 emissions. And the way to do that is to move towards electric vehicles. Many of you may have electric vehicles. And if you do, what you have probably figured out is that if you live in a house and you have a garage and you can charge your car in a garage, that having an electric vehicle is wonderfully convenient because you can plug it in when you get home at night. Note that that's not the best time to be charging your car. You'd like to be charging it in the middle of the day when we have extra electricity, but you can plug it in at night and it'll be waiting for you charged when you are ready to go to work the next day. But if you are one of the millions of Californians that live in an apartment, what you will find and live in an apartment and park on the street is that charging an electric vehicle is a major inconvenience, and waiting for your vehicle to charge is a huge loss of time. California has mandated that by 2035, all new cars sold are going to be electric. And so we're going to have to solve this problem of large charging times before we force everybody to buy electric vehicles. The other place that fast charging is important for is what's called regenerative energy storage. So anytime you have anything that's moving, a train, a weight, a lift, when it goes up, it takes energy to move it up. When it goes down, it can generate electricity from the kinetic energy as it goes down. But in many cases, that energy has to be stored very quickly or it's lost. So this is an example. This is a giant crane that is at a port somewhere in Asia. And if any of you have been to the port of Long Beach or the port of Los Angeles, you know that there's many of these cranes that lift the backs of trucks off of boats and set them on truck cabs that are waiting to take the contents to their final destination. If you've been to the port, in addition to seeing these giant cranes, you know that the entire place smells of diesel exhaust because these cranes generally run on diesel fuel, and they use fuel to lift their weights. And then when they drop them, they just waste that energy. So this crane has a giant box here, which is made of a type of fast charging battery called a supercapacitor that I'll talk about in a minute. And I want you to note that's a car. And so this is a really big bank of batteries, but it is able to store almost half the energy from every lift and use it every drop and use it on the next lift. And so if you can do this regenerative energy capture, you can really cut down on the amount of fossil fuels that you use. And cranes are not the only place that this kind of regenerative energy storage would be useful. In addition to these topics, if you make things that are fast charging, you automatically build in longer cycle life. And I will talk about why that is. In addition, fast charging batteries can help stabilize the whole grid with respect to renewable energy coming on and off the grid because they can take out fluctuations. Okay, so I hope I've convinced you that fast charging is an important thing. We now need to figure out how to make it happen. So if any of you have electric vehicles, you may know that if you take your car and plug it into a normal 12-volt power supply, it takes actually 1 to 2 days to fully charge a car. If you plug it into what's called a level 2 charger, you can fully charge your car in 4 to 5 hours. And if you go to one of those Tesla supercharging stations, you can fully charge it in under an hour. So based on this, it appears that it's just the charging station that determines how fast you can charge your car. So could we just build a super duper charging station and charge all of our batteries in 10 minutes? And the answer to this, unfortunately, is no. Batteries have an intrinsic speed that they can charge. And if you try to charge them faster than that, you can do real damage to your battery. those of you who own a Tesla will be pleased to know that Tesla actually water cools their batteries, actively cools them, which is the reason that you can charge a Tesla at a Tesla supercharging station. But if you don't have that active water cooling, you're pushing your battery far faster than it can go, and you can really damage it. Unless you can make a battery that is designed to charge fast. And that's what we want to talk about. How do you design a battery to charge fast? Okay, so not everybody knows everything about batteries, so I want to start with some basic introduction to battery systems. There's a lot of batteries, and they all look sort of the same. They look like little cylinders, but what's inside can be utterly different. They can be alkaline batteries, nickel metal hydrides, lithium-ion batteries, and they look the same. Okay, so a normal battery, a AA or a AAA, is what's called an alkaline battery. These are not rechargeable, and they are basically just chemical fuel in the form of a battery. They are made up of zinc that you burn or oxidize to zinc oxide, and you do that in a basic solution. Basic means alkaline, and so we just name the whole battery after the pH of the solution that fills up the battery. Lead acid batteries are used in your cars. They are conversion between lead and lead oxide, and they're in an acidic medium. So we call them acid batteries. We chemists are very original in our naming. These are rechargeable, and they actually recharge very well, but they are extraordinarily heavy because they are based on lead. If anyone's tried to change a lead acid battery, you know you can barely lift them, which means they are not good for transportation applications. Nickel metal hydrides have a nickel alloy and a nickel hydroxide. They're also basic. They're rechargeable, but they are very slow and they have poor recharging lifetime. Lithium-ion batteries, even though they may look just like the others, are utterly different inside. They are made of many different materials, and we'll talk about how they work, but they are much more rechargeable and are much faster. So the reason for this difference is that all of these batteries here, as you charge and discharge them, basically every single atom that make up the battery in the cathode and the anode, which are the two parts of the battery, move. You take zinc and you break every single zinc-zinc bond, and you make zinc-oxygen bonds. So you rearrange every atom. For lithium-ion batteries, in contrast, only the lithium moves. And that allows these batteries to be much more reversible and also be faster because you're moving less atoms. Okay, so I want to point out that lithium-ion batteries can look different. They can be pouch cells, they can be cylinder cells, but inside they're all the same. So what makes up a lithium-ion battery? So it's made up of layers, and those layers are wrapped to make a cylinder cell, or they're accordion folded to make a pouch cell. But the layers are composed of a layer of the cathode. We'll talk about what that is. A layer of separator, which is literally plastic with holes in it. Its whole purpose is to keep the anode and cathode from touching and to let the liquid flow back and forth. And then a layer of the anode. So what are these anodes and cathodes? So these are materials that have chemical structures that we're about to talk about, mixed with conductive carbon, so just graphitic carbon, and then some glue, some binder to glue it all together. Of these components, the most colored is the conductive carbon, and so what you make is a black ink of your anode or cathode and literally spread it on a metal foil to build your battery. And the anode and the cathode look the same because they just look like the carbon. So now let's get into the chemistry. What is the difference between the anode and the cathode? So both of these materials have crystal structures, that is, arrangements of atoms that have spaces in them. Those spaces could be layers, they could be tunnels. I'm drawing layers because tunnels are harder to draw in 2 dimensions. And the idea is that the cathode is the material that is stable with lithium in it. The anode is the material that is stable without lithium in it. And between it is a liquid that has some lithium ions in it as well, called our electrolyte. When we want to charge our battery, what we do is we pull an electron out of the cathode and stick that electron into the anode. That creates an electric field, which pulls the lithium out of the cathode and pushes the lithium into the spaces in the anode. Now we have a high energy configuration where all the lithium is in the anode. It's not in the cathode. The electron is in the anode and not in the cathode. The electron wants to be in the cathode. And so if we connect a wire between the anode and the cathode, the electron will spontaneously flow back. That is the electricity that you are using to power your computer or your cell phone or your flashlight. And as the electricity flows back, the lithium ions also flow back from the anode to the cathode. If we ask, what is the slowest part of this process? It is moving the lithium ions in the solid state from between these layers. Once they get to the liquid, they can zoom across, but then they have to move in these tiny spaces between the atom layers, and that's the slowest part. So when we talk about batteries, we can think about two metrics. One of them is energy density. That's how much lithium can you physically stick in the material and how much energy can it store. And the other is power density. That is energy per time. So how fast can we put electricity in or pull electricity out of our battery material? And as I said, that depends on the ability of these lithium ions. We pick lithium because it is the smallest non-reactive ion we can make. The only thing smaller is hydrogen, and it reacts with everything. So it's the smallest thing, so it should be able to move as quickly as possible. But that motion of lithium in these gaps is still the slow step of charging a battery. Okay, so what happens if you try to charge it too fast? I said that the reason the lithium moves is because you've created an electric field. If you want to try to make the lithium move faster, you need to use a bigger electric field, which means applying a bigger voltage. But the energy of that bigger voltage is not used for your battery. It's just wasted as heat. So your battery gets hot. When your battery gets hot, it starts to do chemical reactions. Those chemical reactions shorten your battery life. And that's the reason you can't break the speed limit of your battery. If you want to charge fast, you need something where the lithium ions can move fast. Okay, so to quantify this, we usually draw what's called a Ragone plot. And on one axis, we put the energy density. That's the energy it can store. And on the other axis, we put the power density. That's the speed. So what you see is batteries store a lot, but they're slow. So they're low on the power density. Fast is a parallel plate capacitor. That's just two plates of metal that you charge up. Something that bridges the gap is something called a supercapacitor or an electric double layer capacitor. And this is a high surface area conductor where you charge up one plate of the conductor and then you balance the charge by an ion in solution. So you make a little set of parallel plates at the liquid solid interface. So this is like a parallel plate capacitor, except it has much higher surface area, so much higher energy density. But what we really want is something with all the energy of a battery, but higher speeds. And to get there, we're going to look at something called a pseudo-capacitor. And pseudo is the active word because this is sort of a battery and sort of a capacitor. So what we're going to do is we're going to do the exact same reaction you do in a battery. We're going to say, reduce a transition metal and take a lithium ion and put that lithium ion right next to it. But we're only going to do those reactions near the surface of a material so that that slow diffusion of ion doesn't slow down our battery charging. And what we'd like to ask is, what are the key factors required to produce fast charging pseudocapacitive electron materials? Okay, well, the simplest solution is just to make the material smaller. If it takes too long to move a lithium ion across the 10 micron size, the bulk material that's used in most batteries, convert that material to a few tens to hundreds of nanometers in size, and now the lithium doesn't need to move as far. The problem is if you have little individual nanometer-sized pieces of battery material, it's very hard to move electricity into those materials, and you need to move lithium and an electron into the material at the same time. So to solve that, we make nanoporous or Holey battery materials. And so the idea is we make little building blocks with short diffusion lengths for our lithium ions, and then we have holes that are full of our liquid electrolyte, where the lithium ions can zoom through the holes and make it to all of the reactive sites in our little pieces of active material. Importantly, the entire material is electrically interconnected so that the electrons can get out of the material. Okay, so we use chemistry to make these materials, and we use what is called polymer templating. So we make little nano-sized spheres of plastic, and we make them using self-assembly of block copolymers, or we make what I call plastic mayonnaise. So we do an emulsion polymerization of polymers like standard polymethyl methacrylate to make tiny spheres. And then we co-assemble either molecular precursors or preformed nanocrystals with our plastic spheres to make inorganic organic composites that have our battery material surrounding our plastic. And then we simply burn up the plastic to carbon dioxide and water to leave behind our coals. So it is a very easy way to convert any material into a porous material. It turns out, however, that it is not enough to just make a material small. You also need to make sure that the lithium can move freely through the network. And the problem is the crystal structure. So pretend these lines are lines of atoms. The crystal structure without lithium and with lithium is generally not the same. And so to stuff in lithium, you have to create a little domain called a critical nucleus of the new phase. And then this domain has to propagate or grow through the material. And if lithium insertion is tied to this phase transition, it's unfortunately going to be slow. So let me show you a picture that better illustrates that. Let's say this is our crystal structure without lithium, and this is our crystal structure with lithium. The lithium is small and can move easily, but the heavy atoms are much harder to move. And in order for this lithium to move, the entire phase front has to propagate through the material. What's even worse is this lithium needs to come out here, but the new lithium needs to go in here. And when it tries to move through this domain, every lithium site is full. So there's no easy way for the lithium to move through this domain. If instead of this phase transition between two different crystal structures, we could instead have a more relaxed material that could accommodate every crystal structure, something we call solid solution behavior, we could go from empty to full through a variety of intermediate structures. And now the lithium can easily hop from empty site to empty site and move through our material. And so fast batteries need to charge like this. So let's look at some real data and see if we can convert a battery that is slow to a pseudocapacitor that is fast. So the first system we're going to look at is molybdenum dioxide. This is the tunnel structure material, so it's not layers, it's tunnels. But it has the advantage that it is a metallically conducting oxide. So electrical conductivity is not a problem. And we're going to use it to explore size effects. So this is an electron micrograph of a porous moly oxide phase. And when we try to charge this material, what we find is when we charge it faster and faster, so this is charging time, getting shorter and shorter, we hardly lose any capacity. So we said, okay, this is a good model system that might be a fast charging battery. So we want to make materials with different sizes. And the way we do that is we mix together a little cluster called a polyoxometallate cluster that contains our molybdenum and little tiny spheres of plexiglass that we made in our colloidal mayonnaise synthesis. And then we want to dry them, but we don't want them to demix. So we freeze dry them, just like freeze-dried fruit. We dunk them in liquid nitrogen, and then we use vacuum to pull off the water. And we keep mixed inorganic and organic components. And we can use this to make really beautiful porous powders. So we're going to use 4 samples here. Bulk moly oxide, a large porous material that has 50 to 100 nanometer pores, a small porous material that has 20 or 30 nanometer pores, and then nanocrystals that are only 10 or 20 nanometers in diameter. These are not a perfect architecture. They're not interconnected, but they're the only way to make it really small. And for those of you who know X-ray diffraction, we see that the peak widths steadily broaden as we make our material smaller. Now we're going to look at how fast they charge. And we're doing something called galvanostatic cycling, which is constant current cycling. And what we see is that in purple, the smallest material has the highest capacity. And I have these numbers, 1C, 2C. These are charging rates. So 1C is charged in 1 hour. 2C is charged in 1/2 an hour or 30 minutes. 10C, 6 minutes. 20C, 3 minutes. And what we see is at all these rates, the smallest things keep the most capacity. The bulk in yellow shows the least capacity, and the medium-sized ones are in between. If we look at the actual current voltage curve, we see something else that tells us about phase transitions. If we look at the bulk, we see this plateau. What that means is as we put in more current, the voltage is not changing. This is just like ice in water. If you have a solution of ice and water and you're trying to melt it, as long as ice and water are present, it is locked at 0 degrees C. Once you've melted all the ice, it can heat up. But when you have two phases present, you lock the temperature. So the fact that we have locked the voltage means we have a first order phase transition, just like ice melting to water. As we go smaller in size, these plateaus are replaced by slopes. And the slopes tell us we've gotten rid of our phase transitions. Now, if you're a chemist, you probably don't want to see plateaus turn into slopes. You would like to see structures. And so we can turn to X-ray diffraction. So this is a technique that chemists commonly use to determine the structure of solid materials. And we have many different scattering peaks. I'm showing just one of those peaks here. And we're going to trace it as the material is charged. So we see this peak shifts, and then all of a sudden it jumps to a new position. And that is a phase transition. This is on charge, and then it jumps again on discharge. This is the bulk. As we get smaller, the size of that jump gets smaller and smaller until in the smallest size sample, there is no jump at all. So we have converted a phase transition to a solid solution with size. Okay, so we can use this data and we can actually just say, what's the volume of the material? And what we find is as we put in lithium, the volume gets bigger. That makes sense. We put stuff in, it takes more space. And all of the materials, big, small, medium, are exactly the same until we get to the phase transition. At the phase transition, the biggest sample has a big jump. The medium samples have a small jump, and the small sample has no jump at all. This is a second phase transition, which does the same. And this is the raw data used to generate this. What this suggests is that in this region, all of these materials should be the same. And in this region, the big materials should be much slower and the small materials should be much faster. So we can quantify that using electrochemical kinetics. And if you have not had a lot of chemistry, just close your eyes for about 30 seconds, and then we will get back to you with things that are simpler. So it turns out that when you take cyclic voltammetry curves, you can sweep the voltage at different rates. And if your material behaves sort of Fickian semi-infinite diffusion, you would predict that the current that you would measure varies as the square root of the sweep rate, or the sweep rate to the 1/2 power. For a capacitor, it should vary linearly with sweep rate. And so we can measure this exponent and say, for any given material, is the current that we measure more like a capacitor or more like a battery? So 0.5 is a battery, 1 is a capacitor. So in the bulk, around the phase transition, we find that our exponent is pretty low, 0.69. As we decrease the size of the material, this exponent gets steadily closer to 1, moving all the way up to 0.93 in the smallest sample. If we look in a region where we don't have a phase transition, all of these materials show really high exponents. And so when we have a kinetic limitation, we look like a battery. When we don't have a kinetic limitation, we look like a capacitor. Okay, what does that tell us about the way these things charge? In bulk materials, we have two-phase coexistence where we have phase boundaries and motion of the phase boundary, and that makes bulk materials slow. Nanocrystals are really fast because they show that solid solution behavior. But I actually showed you that the medium-sized samples were pretty fast as well, but they did have a phase transition, a discontinuous jump. How can we make sense of that? The answer is probably they never have a phase front that's moving like this. Instead, individual nanocrystals sort of transform at once, and that jump is because of the variation in our sample. But both of these two mechanisms are really fast. Okay, how does that help us with our cost of energy storage? Well, if you don't have phase transitions, you don't rearrange the atoms every time, and that results in much longer cycle life. And so if you look at the bulk material, after 1,000 cycles, it's lost 50% of its capacity. If this was your cell phone and you charged it every night, that would be 3 years and your battery would be pretty useless. The nanoscale materials, after 1,000 cycles, still have 90% of their capacity. Okay, let's look at another system that's also a super fast charging system. This one, again, is based on molybdenum, but this time we make a sulfide, not an oxide. So for those of you who think about chemistry, sulfur is a big atom, it's sort of blobby. It doesn't really interact with lithium very well. And so lithium can move very quickly between the layers of moly sulfide. The problem is it's hard to make moly sulfide small because when you start to make it, it grows big sheets. So in this work, what we did is we made nanocrystals of moly oxide and then converted them to the sulfide. And the layers of the moly sulfide just sort of stuffed themselves into our nanocrystal any way they could. And then we assembled those into porous networks. This material is blazingly fast. So I went up to 20 C, 3-minute charge before. Now we're going up to 100 C, or a 36-second charge, and the material has half its capacity in a 36-second charge. That's really fast. This material has a phase transition, and in the bulk, you can see that that phase transition is indicated by the appearance of this extra peak when we put lithium in it. So we're charging and discharging here. And we see that a new peak appears in the bulk. In the nanometer scale system, there's no peak. And this is just this is one of our batteries that has an X-ray window put in it so that we can actually take X-ray diffraction on our battery while we cycle it. So we'd like to use this system to learn about the effects of size and disorder on controlling fast charging. And we take advantage of the fact that we make our sulfide from an oxide to control the disorder. So we control the size by the size of the oxide that we start with. If we want little MOS2, we use little moly oxide to start. And if we want big MOS2, we use big moly oxide to start. But if we want to make it disordered, we do this conversion at a low temperature. And this is X-ray diffraction. It's, again, that probe of structure. And what we see is that our diffraction peaks are very broad when we do it at low temperature. That means it's a disordered phase. When we do it at high temperature, our diffraction peaks are very narrow. So we can now make a grid of small, disordered, small, ordered, large, disordered, and large, ordered, and look at how that controls the ability to charge quickly. Okay, there's a lot of wiggly curves here. You don't have to pay attention to many of them. We characterize the disorder using X-ray pair distribution function analysis, which is a total scattering technique that lets us look at the ordered and disordered components of a material. And what we find is that compared to bulk material, all of our nanomaterials are a little bit disordered, but the ones that we made at high temperature, that is the green ones and the pink ones, have mostly just one kind of disorder, which is where the layers slide. So they get a little bit on a registry. That could make it hard to have a phase transition, but that doesn't do much else. The ones that are made at low temperature have sliding, but they also have expanding. So the layers are far apart. So disorder makes bigger pathways for lithium to move. Crystalline just makes it so that the crystal structure isn't so perfect. So we can take data as we charge faster and faster on all these samples, but they actually have slightly different capacities because of the surface reactions. And so it's better if we just normalize them to their starting capacity. And what we see here is that the bulk sample is the slowest. The next slowest is the one that is large and crystalline. So it's the closest to a bulk crystal. The fastest one, the one that keeps the highest capacity as we go fast, is the one that is both small and disordered. And then interestingly, the small and crystalline and the large and disordered are almost identical. And so what this says is that disorder and size can both equivalently be used to make materials charge faster. We can do another one of those kinetic analyses. We're doing basically the same assumption where we say batteries are things that have currents that varies sweep rate to the 1/2 power. Capacitors have sweep rate to the linear power. And then we actually can decompose the entire CV curve into 2 components. And we can say, what fraction of the total stored charge is capacitive? So on these graphs, if it's colored, any color, it's a capacitor. And if it's white, it's a battery. And what we see is there is the most white on the things that are large and crystalline. There is the least white on the things that are small and disordered. So this is 90% capacitive. This is 76% capacitive. And then again, we see that things that are small and crystalline or large and disordered have about the same amount of white, and they're both about 80% capacitive. So size and disorder can equivalently make things charge faster. We can do that X-ray diffraction experiment, and what we see is only the biggest, most crystalline samples have phase transitions. Both size and disorder can suppress those phase transitions. And so overall, what our take home is you might say disorder, isn't that bad for lithium moving through a material? But both size and disorder can be used additively to suppress phase transitions and turn battery materials into fast charging pseudocapacitors. Okay, so I said not having phase transitions makes things cycle longer. Does that also work with this system? And the answer is yes. We see incredibly long cycle life in these molybdenum disulfide systems. This is 10,000 cycles with almost no loss in capacity. And this is really what you need for grid level storage. When you build a battery into grid level storage, you want it to be able to cycle again and again without having to pay the money to replace that battery on the grid. Okay, so this is great. This is research. How do you turn research into real products? The answer is you try to start a little tiny company. And so I had the pleasure to help found a little tiny company called Battery Streak, whose motto is charging lightning fast. And the idea is to try to commercialize some of these materials. And Battery Streak is working on many, many different kinds of material systems that are all basically nanoporous and Holey materials. But I want to show one piece of data that they collected. And this is data on what happens when you try to charge a battery that is made to charge fast quickly, or a battery that is not made to charge fast quickly. And so this red line here is a conventional Panasonic 18650 is a standard pouch cell or standard battery size. And if you try to charge it at 2C, that's a 30-minute charge. We're not talking the 3 minutes or the 30 seconds I was talking to, a half an hour charge. That battery heats up to above 50 degrees Celsius. So remember, body temperature is 37 degrees Celsius. So this is hot enough it would actually burn you if you touch it, okay? So half-hour charge, you get a burning hot battery. If instead you take one of these porous Holey batteries and in white, we charge it fast and discharge it slowly, it goes from room temperature to a calm little 30 degrees. That's barely warm to the touch. If you charge it fast and discharge it fast, it heats up a little more, but it is still way below body temperature. It's only up to about 33 degrees. And so if you take a battery that's designed to charge fast, you can charge it incredibly fast and it will not get hot. Okay, I have about 5 minutes left. And in those 5 minutes, I want to entirely change gears. So we're going to leave energy storage behind. And we're going to talk about another use of Holey or porous materials. And this is a concept that is hopefully a part of our clean energy future, which is something called passive daytime radiative cooling. And when I first heard about this, I thought this must be voodoo, not science. But it actually works. Okay, so if we ask what controls the temperature of our planet? The idea is that energy comes in from the sun, and that energy heats up our planet. At the same time, we would just turn into a we would cook if there was no way to get rid of energy. But there is. We can emit IR radiation to the cold vacuum of space. And there's lots of space and it's very cold. And so it can take as much IR radiation as we can give. We have an atmosphere, however, and that atmosphere only lets certain wavelengths of IR radiation pass through. And so there is something called an atmospheric transparency window where heat gets out of the planet. If you can design a material to not absorb sunlight and to strongly emit IR light, you can create a material that will spontaneously cool down in the sunlight. And I didn't believe this until we made them. Okay, so what is the idea? Here is the solar spectrum. So this is wavelength in microns. We have to pick microns because we're going over a very big range. Here is the visible, sort of 400 to 700 nanometers, or 0.4 to 0.7 microns. And the solar spectrum goes into the near IR. So you want something that does not absorb any light in that region, and in fact, actively scatters away all of the light that comes from the sun. Then in the far IR region, there is something called an atmospheric transparency window from 8 to 13 microns, which is where the atmosphere can actually pass IR light. And remarkably, that is also where a black body that is the temperature of the Earth, that is 300 Kelvin, emits. So if you can create a material that has very strong emission in this region, it will emit IR light and cool down. So what's a strong emitter in this atmospheric transparency window? It turns out that silicon dioxide, silica glass, is a super strong emitter. So you might say, okay, great, make the whole world out of glass. The problem is silica is such a strong emitter that its refractive index goes way up near its absorption and emission. The ground state absorption and emission are reverse processes. And its refractive index goes up so high that it becomes reflective. And the result is it's not a strong emitter when it's a reflector. So what we need to do to make silica work as our IR emitter is we need to lower its refractive index. And we can do that by making it porous. We basically need to have less silica in any one space. And so what we want to create is silica glass in a porous network so that it can strongly emit IR light. And then we're going to embed in it big spheres of silica glass where the size is picked to scatter all of the incoming sunlight. And so our goal is to scatter away the sunlight and then emit heat to the vacuum of space. So this is our cartoon. It's all glass, silica, a porous network, and big scattery spheres. So here's our material. They look white. That means they're scattering light. On a big length scale, 20 microns, they look homogeneous. As you zoom in, you can start to see those big scattering colloids. As we zoom in more, we can see one colloid embedded in a porous network. And then as we zoom in more, we can see this whole porous network of silica. So this is our daytime radiative cooling material. And we take this and we measure how much light it reflects. And we find it reflects basically all of the light in the solar spectrum. And then we look how much it emits in the atmospheric transparency window, and its emission is basically 99% in the region where we can get light out. So it's a great emitter and a great scatterer. And then we go to the roof. And we live in Southern California, so we have lots of sunlight, and we build a little setup where we try to keep heat from leaking in from other places. And we put our sample in a little insulated cup, and we measure the temperature of the cup. We measure the temperature of the whole setup, and we measure the temperature of our porous silica material. And we find it is consistently at least 5 degrees below the cup and about 10 degrees below the overall setup temperature. So this material is spontaneously cooling, sitting on the roof in the bright, bright Southern California sunlight. Now, our material is porous, which means it's an insulator, and we actually measure the temperature at the bottom of the sample, underneath it. And so in theory, the top should be even cooler. And so if we measure the top, we indeed find it is almost 10 degrees cooler than the bottom. This is when we just take a sample at room temperature and put it in our little setup and measure the temperature. This one is interesting because here we take and we put a sample in the refrigerator, we cool it down, and then we take it out and we put it in our setup. And we find that the top does not heat up at all. So we got it cool and it stays cool because it sends any incoming heat out to the vacuum of space. So this kind of material is really well suited to keep things cold in the sunlight. So imagine you were in the desert and things got cold at night and you cooled them down, and then you could surround them with your radiative cooler and you could actually keep them cool during the day without using any energy. So we have related projects for putting on buildings and windows, but as an idea, I hope this shows you how porous materials can also help with building efficiency. Okay, so I think I'm out of time, and so let me conclude. I hope that I've showed you that you can't make batteries charge faster just by building a bigger charging station. Instead, what you need to do is optimize the nanostructure, and that this can create batteries that really can charge very fast. The first key to making them charge fast is simply make the lithium move less far, so make nanostructured versions of the material. And the second key is to get rid of those phase transitions that keep the lithium ions from moving freely into and out of the material. We can get rid of those phase transitions either with small size or by adding disorder to our material. And if you make your battery right, it can charge really quickly without getting hot, and it can also show very long cycle life. And then finally, at the end, I gave you just a little teaser on porous materials for daytime radiative cooling, that we can actually create materials that we can put in the bright Southern California sun and have them get spontaneously cooler. I didn't do any of this. I have the most phenomenal research group, and I really want to thank them for all of the research that they have done. My group does a lot of things, energy storage. We have other projects on high energy batteries, on sodium ion batteries. I only talked about one kind today. We also work with organic electronics, nanomagnetics, new super hard materials. But for this, let me just thank the fast charging battery team. All of these people contributed, but I want to really call out Danny Robertson and Yi Yao, who took a lot of the data that I showed you today, along with a bunch of help from Helen Cumberbatch. My collaborators were Bruce Dunn and Johanna Nelson Wicker, and this was mostly paid for by the Department of Energy with a little bit of help from Battery Streak. And I need to tell you all that Sarah Tolbert has a financial interest in Battery Streak. Our energy efficiency radiative cooling work was done. What I showed you here is done primarily by Susan Ju, also with some help with Natalie Kasansky, and our collaborators are Laurent Pilon, Aswath Rahman, and Bruce Dunn, and this was funded by ARPA-E. Before I end, I want to just give you a little bit of sense. Everybody looks very nice and well behaved in these pictures, but my research group knows how to work super hard, but they also know how to have fun. And so every year we have our annual picture to look silly. So one year we were Where's Waldo? And we have a whole series of Waldo hiding himself in our research group. This was summer in Southern California. For those of you who are in Southern California, you know that as the temperature gets cold, we put on our wool sweaters, we put on our hats, we may even put on our snow boots, but we don't stop wearing our shorts, and mostly we don't stop wearing our flip-flops. So this is our summer in Southern California. My favorite is when we were Minions and I got to be Gru. And then this year we were Barbenheimer. So thank you to my super fun research group, and I am happy to take any questions.
Apart from the subject, I just wanted to know, Sarah, whether you will entertain any high school students who is just about to complete their high school level or in the transition between high school and entering the undergraduate level.
Whether I can take them as research associates?
Yeah.
So I have a lot of chemicals in my group that are not the most friendly. And so I don't generally take high school students into my research group. I have very occasionally, but I try not to, just for safety reasons. But I do actually run a summer program for high school students through our Nano Institute, where we talk about a whole bunch of nanoscience-inspired technologies. And that's actually a summer program for high school students. And so I definitely would encourage people to look into that.
Thank you. Any other question from anybody else? I have a
know it's
silly
on-
question actually. Can you replace lithium with sodium? I think sodium is a bit cheaper than lithium. Is it possible?
Well, so I am the director of a new DOE center that we call STORE, and it stands for Strain Optimization for Renewable Energy. And the whole goal of that center is to build sodium-ion batteries. And the problem is sodium is much bigger than lithium. And so when you put sodium in, all of the other atoms move around and they create very large strains. And the result is that even though sodium is so much cheaper than lithium, if you include the lifetime of the battery, it turns out that sodium is not cheaper because the cycle lifetime is so much shorter. And so what our center is trying to do is actually create sodium-ion batteries that will cycle as well as lithium-ion batteries so that the reduced cost of sodium will actually buy you something in terms of grid level storage. Lithium is never going to work for mass grid level storage. It's just too expensive. It's great for transportation, but it's not going to be a solution to the huge amount of storage we need to go from daytime solar to powering evenings and all the way through the night. So we're going to have to come up with some cheaper chemistry, and sodium is definitely one of the options.
That's great. And Glendy Ramirez from the Francisco Bravo School, whose research students are listening to you, she wants to know what is the summer research program, and can we get some details from you on the summer research program, the name of the program, and all that? So
it's not a full summer research program. It is actually summer nanoscience classes. So there are two different, they are summer sessions classes for high school students, and there are two different programs. One is called Nanoscience Lab and one is called Applications of Nanoscience. And they're an opportunity to do sort of a series of cutting edge nanoscience experiments to explore some of the cutting edge characterization equipment that's at UCLA. The applications of nanoscience also has an entrepreneurship component. So you think about how you can use nanoscience for product development and learn something about entrepreneurship. And the Nanoscience Lab is just pure science. But the California Nanosystems Institute, CNSI, has information on those programs. Or you can send me an email and I can try to find the link, but I don't know where it is.
Okay. So if there are no further questions, it is my great pleasure to thank Sarah for a wonderful seminar. I was particularly impressed by the change from oxygen to sulfur can cause that much of favorable response and all that. And that's very, very interesting. And the silicon nanoparticles, that's again is a very, very interesting aspect as well. And I thank Sarah for a wonderful seminar, very educative seminar. And I also thank the audience, including the Francisco Bravo School research group students who are attending right now. And I thank SCALACS for giving us the opportunity, and the National LSAC Committee, the Local Section Activities Committee, for giving us a grant that enabled us to organize this function. Thanks, everybody. Thank you.